Okay, this is our last section in Chapter 11. We're going to start by looking at what we call standard position. Okay, when we draw an angle in standard position, and we typically are only looking to draw positive angles, right? When we draw positive angles, we are drawing them counterclockwise. So standard position is where we start here at 0 degrees. Okay, up here would be a 90-degree angle. Over here is 180, down here is 270, and then 0 is the same as 360. Okay. Remember too that this is quadrant 1, this is quadrant 2. We tend to use Roman numerals to number our quadrants, and there's quadrant 4. Now, if we were to draw a circle around here, centered at the origin, okay, and suppose we were to draw an angle in standard form. So this is known as the initial side, right? The side that rests on the x-axis, that's the initial side. This is called the terminal side, right? It's where it's terminating or ending, okay? Let's suppose we call this angle theta. And notice that right here we have a point on our circle. Now if we were to drop a vertical line here and make a right triangle out of this, this horizontal distance is x. Okay, it just goes to where the triangle ends, and then this vertical distance is y. So that would make this point x comma y. Alright, so notice that if we were to focus it on x for a moment, x is an adjacent side, alright, and if this is a unit circle, okay, let's suppose, I should have said this initially, let's suppose that our radius in this circle that I drew was 1. Well, if we were to look at x, well, isn't it true that the cosine of our angle would be x over 1, right? Because it's the adjacent side over the hypotenuse. So what that means is our x distance here is the same as the cosine of theta. Likewise, our y distance, okay, this is going to be the same as the sine of theta. All right, so if you're not quite seeing that, again, for the cosine one, cosine of theta is equal to the adjacent over the hypotenuse. The sine of theta is equal to the opposite side over the hypotenuse. Well, since the hypotenuse is 1, what we have here is for x, that's represented by cosine of the angle, and for y, we have the sine. All right. Okay, so now if we were to take this triangle and draw it in every quadrant, all right, let's start in quadrant 2. All right, this would now be negative x comma y, all right, which really means that we would have negative cosine of theta comma sine of theta. So notice how the cosine would be negative in that quadrant. Down here, again, if we were to just make a right triangle out of this, all right, so we're still talking about this same unit circle, the same triangle with a radius of 1. This would be negative x, negative y. Notice here you would have negative cosine of theta, negative sine of theta. So both sine and cosine are negative down there in that quadrant. Let's do it in the fourth quadrant here. Down here we would have x comma negative y. Alright, so this means that it'd be the same as cosine of theta and then negative sine of theta. Notice how cosine is positive and sine is negative. Well, we can summarize what's positive and what's negative by using this A, S, T, C, which stands for the A is all of the trig functions are positive. Now let me back up for a moment. Recall that we said that the tangent function is sine divided by cosine. So keep that in mind as we go through this. All right, so in the first quadrant, they're all positive. So how do we know tangent's positive? Well, the sine divided by the cosine, tangent would be positive as well. So the A stands for all three are positive. The S stands for only the sine is positive. You can see here that the sine is the only one positive. All right, so just a quick reminder, let's just write it down. I know I said it, but let's just write it. Okay, we know that tangent is sine over cosine. So if I take a positive sine here and divide it by a negative cosine, you're going to get a negative tan. So only sine is positive in the second quadrant. Third quadrant, only tangent is positive. That's because if you do a negative sine divided by a negative cosine, you get a positive, right? So tangent would be positive. Finally, down here in the fourth quadrant, only cosine is positive. Both sine and tangent would be negative. All right, so just to take it a step further, suppose this were a 45-degree angle. If you were to do the sine of 45, the cosine of 45, the tangent of 45 in your calculator, making sure you're in degree mode, you'd see that they're all positive. Let's go to the second quadrant. Suppose that this angle here that is formed, okay, from the x-axis, suppose that's 135 degrees. Punch in the sine of 135, cosine of 135, tan of 135. Again, you would see that the cosine one is negative, the tangent one is negative, only the sine one would be positive. Likewise down here, pick an angle like 225 degrees, okay? A 225 degree angle is down here in the third quadrant. If you did the sine of that, the cosine of that, and the tangent of 225, you'd see that only the tangent one was positive. And finally down here, something like 315, right? It's somewhere between 270 and 360, right? So pick any angle, all right, such as 315. If you were to punch that into your calculator, do the sine of 315, the cosine, and the tangent of 315, you would see that only the cosine one was positive, okay? So know where angles are positive and where they're negative. And again, this ASTC is a nice way of summarizing where things are positive. Okay, here's an example where we're going to use this information. So suppose we have a diagram here. We know that this distance is 1. This is our angle theta. We have this circle that would be going around, okay, but we just see part of it drawn in the first quadrant. We're told that our angle theta is 50. We're looking to find this point, or the coordinates for x comma y. So we want to find the values. So you have to know that this correlates to the cosine of the angle, so the cosine of 50, and then the sine of 50, okay? So that's not a nice special triangle value, so you would go right to your calculator. Okay, so if we used our calculators, what we would have if we punched in these values, or perhaps a question asked for the exact values, if that's the case, cosine of 50, sine of 50 would be your coordinates for x and y. All right, let's work backwards this time. We're looking at the same picture as up above, but this time we're looking to find the angle theta, all right, if we're told that xy has these coordinates. Well, from this x value of 0.970, remember that the x corresponds to cosine. So to get that, what we're going to need to do is to inverse cosine, right, to reverse it. All right, and likewise, if you remember that the y value correlates to the sine, all you have to do is do inverse sine, okay? Now, for each of these, all right, you're going to get the same answer, okay? Remember that the theta, this is really the cosine of theta, this is the sine of theta, so it's the same angle that we're talking about. So technically, you really just need to do this for one of these. Well, you would see that it's 14 degrees. Most likely it's a nice integer. We're not going to worry about 3 sig figs since these values up here are chopped. Okay, they're rounded. So we can conclude that our angle to the nearest degree is 14. Okay? You can certainly check it by just doing the cosine of 14 and then the regular sine of 14, and you would get these decimal values. Okay, so we'll just make it clear that theta is 14 degrees. Okay, so let's consider a situation now where we have our axes, we have a unit circle drawn, and suppose we have a line that is drawn through the origin. Okay, so it's going through the origin here, and it's making an angle with the x-axis just like before. Okay, so this line would take on the form y equals m times x. Now, usually it's mx plus b. The b is 0 since it's going through the origin. Well, I want you to take a look at what the slope of this line would be. Well, if we were to focus on a right triangle here, okay, we said this is our x distance, this is our y distance, right? Well, we also said that for this point x comma y, that's the same as cosine of theta sine of theta. And since slope is change in y over change in x, our slope here of this line can be represented by sine of theta over cosine of theta. Well, that's really the tangent of theta, okay? So let's write this out and summarize it. So for any line y equals mx, which forms an angle of theta with the x-axis, the value of m, which is our slope, would be the tangent of theta. So how might we see this used? Well, suppose we are asked to find the gradient, which, by the way, IB loves to use that word, just a fancy word for slope, of this line below. So all we know is that it's passing through the origin and that it is forming an angle of 55 degrees with the x-axis there. Well, to find our slope, which we said is really m, right? This is simply going to be the tangent of our angle. Okay, so if you put that into the calculator, 1.43 would be the slope of that line. And that certainly seems reasonable based on the fact that it's going uphill. Okay, so a neat application of trig. All right, so this is like I think the 8th video I've made today. Today is Veterans Day. Using the time to make these videos. Now it's time to rest. Okay, bye-bye.